Another family of supervised learning models that's related to linear classification models is the naive Bayes family of classifiers, which are based on simple probabilistic models of how the data in each class might have been generated. Naive Bayes classifiers are called naive because, informally, they make the simplifying assumption that each feature of an instance is independent of all the others, given the class. In practice, of course, this is not often the case. Features often are somewhat correlated. For example, in predicting whether a house is likely to sell above the owner's asking price, some features, such as the area of the interior rooms, are likely to be correlated with other features, such as the size of the land that the house is built on or the number of bedrooms. And these features, in turn, might be correlated with the location of the property, and so on. This naive simplifying assumption means, on the one hand, that learning a naive Bayes classifier is very fast because only simple per-class statistics need to be estimated for each feature and applied for each feature independently. On the other hand, the penalty for this efficiency is that the generalization performance of naive Bayes classifiers can often be a bit worse than other more sophisticated methods, or even linear models for classification. Even so, especially for high-dimensional data sets, naive Bayes classifiers can achieve performance that's often competitive to other more sophisticated methods like support vector machines for some tasks. There are three flavors of naive Bayes classifier that are available in scikit-learn. The Bernoulli naive Bayes model uses a set of binary occurrence features. When classifying text documents, for example, the Bernoulli naive Bayes model is quite handy because we can represent the presence or absence of a given word in the text with a binary feature. Of course, this doesn't take into account how often the word occurs in the text. So the multinomial naive Bayes model uses a set of count-based features, each of which does account for how many times a particular feature, such as a word, is observed in a training example like a document. In this lecture, we won't have time to cover the Bernoulli or multinomial naive Bayes models. However, those models are particularly well suited to textual data, where each feature corresponds to an observation for a particular word. And so you'll see naive Bayes again, including the Bernoulli and multinomial models, in more depth in the text mining part of this specialization. This lecture will focus on Gaussian naive Bayes classifiers, which assume features that are continuous or real-valued. During training, the Gaussian naive Bayes classifier estimates, for each feature, the mean and the standard deviation of the feature value for each class. For prediction, the classifier compares the features of the example data point to be predicted with the feature statistics for each class, and selects the class that best matches the data point. More specifically, the Gaussian naive Bayes classifier assumes that the data for each class was generated by a simple class-specific Gaussian distribution. Predicting the class of a new data point corresponds mathematically to estimating the probability that each class's Gaussian distribution was most likely to have generated the data point. The classifier then picks the class that has highest probability. Without going into the mathematics involved, it can be shown that the decision boundary between classes in the two-class Gaussian naive Bayes classifier in general is a parabolic curve between the classes. And in the special case, where the variance of each feature is the same for both classes, the decision boundary will be linear. Here's what that looks like typically on a simple binary classification dataset. The gray ellipses give an idea of the shape of the Gaussian distribution for each class, as if we were looking down from above. You can see the centers of the Gaussians correspond to the mean value of each feature for each class. More specifically, the gray ellipses show the contour line of the Gaussian distribution for each class that corresponds to about 2 standard deviations from the mean. The line between the yellow and gray background areas represents the decision boundary, and we can see that this is indeed parabolic. To use the Gaussian naive Bayes classifier in Python, we just instantiate an instance of the Gaussian NB class and call the fit method on the training data, just as we would with any other classifier. It's worth noting that the naive Bayes models are among a few classifiers in scikit-learn that support a method called partial fit, which can be used instead of fit to train the classifier incrementally in case you're working with a huge dataset that doesn't fit into memory. More details on that are available in the scikit-learn documentation for naive Bayes. For the Gaussian NB class, there are no special parameters to control the model's complexity. Looking at one example in the notebook from our synthetic to-class dataset, we can see that in fact the Gaussian naive Bayes classifier achieves quite good performance on this simple classification example. When the classes are no longer as easily separable as with this second, more difficult binary example here, like linear models, naive Bayes does not perform as well. On a real-world example using the breast cancer dataset, the Gaussian naive Bayes classifier also does quite well, being quite competitive with other methods such as support vector classifiers. Typically, Gaussian naive Bayes is used for high-dimensional data, when each data instance has hundreds, thousands, or maybe even more features. And likewise, the Bernoulli and multinomial flavors of naive Bayes are used for text classification, where there are a very large number of distinct words as features and where the feature vectors are sparse, because any given document uses only a small fraction of the overall vocabulary. There's more in-depth material on the Bernoulli and multinomial naive Bayes classifiers in the text mining portion of this specialization. It can be shown that naive Bayes classifiers are related mathematically to linear models, and so many of the pros and cons of linear models also apply to naive Bayes. On the positive side, naive Bayes classifiers are fast to train and use for prediction, and thus are well suited to high-dimensional data, including text, and to applications involving very large data sets where efficiency is critical and computational costs rule out other classification approaches. On the negative side, when the conditional independent assumption about features doesn't hold, in other words, for a given class there's significant covariance among features, as is the case with many real-world data sets, other more sophisticated classification methods that can account for these dependencies are likely to outperform naive Bayes. And on a side note, when getting confidence or probability estimates associated with predictions, naive Bayes classifiers produce unreliable estimates typically. Still, naive Bayes classifiers can perform very competitively on some tasks and are also often very useful as baseline models against which more sophisticated models can be compared.